Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Hoping, dear students, you all will be doing fine. In the last recorded lecture, we discussed the Newton-Raphson method, that is a power flow method for determining the variables or the parameters on the different buses in a network. So we discussed before this method the Gauss-Seidel method, and then we also solved 3 different problems. So in the last recorded lecture we talked about the other method, or the second method, that is a Newton-Raphson method, and then we even developed the general form or the general algorithm for solving power flow problems using Newton-Raphson method. And I in the end also mentioned that we will learn the method in a better way by solving problems. So let me quickly revise the contents of the last lecture. I will quickly go through the contents, and then we will solve a problem using this particular method. So if you remember, we in the beginning discussed that doesn't matter whether it's a Gauss-Seidel method or it's a Newton-Raphson method. In the beginning we estimate the values, or we make a guess for all those values which we don't know. So in the beginning we make a guess for the angles and for the voltages, depending on obviously the number of buses in a particular network. And afterwards in this method we solve the power flow equations. We solve the power flow equations based on the estimates. So we make an initial guess, and then the second step is to solve these power flow equations based on those estimates, and we know the general form of the power flow equations. So the next step is to solve the power flow equations based on the estimates, and then once we calculate the active and reactive power based on the initial guess, we then also calculate the error in the what we also call power mismatch, because we know these powers on load buses. So with the initial guess we calculate the values, subtract it from the known values, and we get the error. And if you remember, even I mentioned that in the Newton-Raphson method we make an initial guess, and then we find the error in the guess, and all these steps in this particular method we follow it to determine the error in the initial guess, that is the error in the angle and the error in the voltage. So all these steps are followed for calculating the error that we add to the initial guess to get the next estimate. So but anyhow, for calculating the error we have to follow all those steps. So after calculating the active and reactive power using the initial guess, we calculate the power mismatches, and once we know the power mismatch, then we discussed it yesterday. Once we know the power mismatches, these are basically the expression for the power mismatches. We write them in the Jacobian, in the matrix form. And this matrix with our having 2 cross 2 in elements, we call this matrix the Jacobian matrix. So once we know the power mismatch, the next step is to calculate the Jacobian matrix. And if you remember here, the derivative of the active and reactive powers are involved. So we will afterwards we will calculate the Jacobian matrix having 2 cross 2 in elements. Then we after calculating the Jacobian matrix, because uh, even this this form of expressing the power mismatches, so this form can also be written in the compact form, and we discussed it yesterday that these are the power mismatches representing the matrix on the left side of the equality sign, and on the right side we have the Jacobian matrix and in the errors in the voltages and in the angles. So in the compact form it can be written in this way. These are this term represent the power mismatches. Then we have the Jacobian matrix, and then we have the error in the voltage magnitude and in the angle. So from that we will then, because we will calculate the power mismatches, we will also determine the Jacobian matrix, and if we know these two, we can determine the error, what is basically important for getting the next estimate. So we will take the inverse of the Jacobian. Knowing these values, we will get the error. So the next step is to take the inverse of the Jacobian matrix, and once we know the Jacobian matrix and the inverse of that, we multiply it with the power mismatches and we get the error. And once we know the error in the voltage as well as in the angle for different buses, we add it to the first estimates and we get the next estimate for the angle as well as for the voltage, and then we will repeat this process to get the next estimate. So this was basically the revision of the lecture that we discussed or we covered in the last recorded lecture. So now we will try to learn this method in a better way by doing exercises. So now I will solve a particular problem using this method. So let me first show you the problem. So now I hope you remember this is also the problem that I gave you in the mid exam, exactly the same problem, and I asked you to solve that problem for 2 iterations using Gauss-Seidel method. Now we will solve the same problem using Newton-Raphson method. So this is the problem having 2 buses. One is the load bus, one is the slack bus. In between we have a transmission line having only inductive reactance, or in other words we have only susceptance, that is once we take the or we calculate the impedance. So bus 1 is the slack bus, bus 2 is the load bus, where the active power consumption and the reactive power consumptions are given. The active power consumption is 100 megawatt, the reactive power consumption is 0 megawatt. So we will calculate the voltage U2 and angle psi 2 using 2 iterations of Newton-Raphson power flow method. So that is what we are supposed to do. Also, we are supposed to make all the calculations in the per unit, because these values are given in the in the SI, what we call SI units. Or so we have a 220 kilovolt at the sending end, and we have the inductive reactance of the transmission line, that is 150 ohm, and we also supposed to take the base voltage as 220 kilovolt and the S base, which is the the parent power base as 100 MVA. So we are supposed to make all the calculation in the per unit. So let me start solving this problem. Another task which is not mentioned here is that let's say this is task 2, and the task 1 is to write the power flow equation. So this is task 2, and the task 1 is to which is not mentioned here, but anyhow let me write it here. The task 1 is to write power flow equations. So write power flow equations for active and reactive power, for active and reactive and reactive powers, for active and reactive powers. So we are supposed to write the power flow equations for active and reactive power at the load bus. So we are supposed to write the power flow equations for P2 and Q2 to represent the bus number 2, which is the load bus. So in this particular task we are supposed to write the power flow equations, and then we have to calculate the voltage and the angle at the load bus using Newton-Raphson method, and we have to solve the problem for 2 iterations, and all the calculations are supposed to be done in per unit. So this is the problem, and I mentioned that this problem you have already solved in the mid exam. So now we will solve this problem, and we will at the end also compare the results that we get from the Newton-Raphson method and from the Gauss-Seidel method. So let's now start the solving the problem, and in the beginning I will convert the values into the per unit, and then we will proceed with the two tasks. So now let me start solving the problem. As the values were given in the SI units, so let me first convert them into the per unit value. So we will solve a problem using Newton-Raphson method. So for task A, let me even put the solution here. We are solving this problem using Newton-Raphson method, and if you remember, we know that because for even writing the power flow equations, let me even write the general form, and as we know that this transmission line have only inductive reactance, so the power flow equations can be written like that. But even before that, let me convert the values into the per unit. So we know that because for power flow equations, to write power flow equations we need the admittances. So for admittance, we have to first convert the given impedance into the admittance. So let me first find the admittance matrix, because that is the first step. You know that quite well. So now the Z base, we know that for converting values into the per unit, the actual value should be divided by the base value, and we know that the base impedance is equal to the base voltage square divided by the S base, and the base voltage, it is already mentioned here, take it as a 220 kilovolt, and the S base as 100 MVA. So now using the given values, it will be equal to 150 square divided by 100. So that will become 484 ohm. So this is the base impedance. And now, as the given problem have a transmission line with only inductive reactance, so we will get the XL in per unit. That will be equal to the inductive reactance in per unit will be equal to it's also 150. The sorry, I made a small mistake. The base value is 220 kilovolt, so that is not 150, rather it is 220 kilovolt. So that is 220 kilovolt. Let me correct it. That is 220 square of that. and 100. But this I mean this is the value of the, one can check it, that is the value of the base impedance. So now let me find the per unit inductive reactance that will be equal to the given value, which is 150 ohm. So 150 divided by 4 at 4 will be equal to 0.309, and we know that with the inductive reactance J is involved, so that will be equal to J is 0.309, but anyhow this is the value of the inductive reactance. So now YL, meaning to say that only because it has only inductive reactance, so this is the admittance, and we know that that will be equal to 1 over ZL or 1 over XL, because then I mean because the resistance is 0, so these are the same, so that will become equal to, if one take the inverse and knowing that it will be equal to 1 over J 0.309, so that will become minus J 3.22. So that will be the admittance of the transmission line. Now we are supposed to formulate the bus admittance matrix. We know that it is a 2 bus system, so that will be a 2 cross 2 matrix. With the entries we have already discussed it. The first entry will be equal to the sum of the admittances connected to bus number 1, so that will be equal, that is only this term, so it can be written as the same, I mean this is minus J because there is only one transmission line, so that will become, and now the second entry is the negative sum of the admittances connected, which is Y12, that will be the negative sum of the admittances connected between the two buses. So with the negative sign multiply with this negative, it become positive, so that will be J 3.22. and if you remember we discussed that the bus admittance matrix, it's a symmetrical matrix, so these two entries will be the same. And now Y22, which is the last entry of the matrix, will be equal to the sum of the admittances connected to this particular bus, which is also the same as this one. So now this will be minus J 3.22. So now this is the bus admittance matrix, and we have calculated, or we have determined the entries or the elements of the bus admittance matrix. So afterwards, now we will proceed to the task, and the first task is to write the power flow equations. But even before that, let me mention here that the P2 in per unit, as it is given, the P2 is equal to 100 megawatt. So the P2 in per unit, the P2 in per unit, P2 per unit will be equal to the actual value, which is P2 divided by S base, as both have same value, so that will become 1 per unit. So this will be 1 per unit. So that is 1 per unit, as both have the same value, 100 megawatt and 100 MVA. So now this is in the per unit. So now the first step is to write the power flow equations. We are supposed to write the power flow equation. That is the first task, and the second task is to calculate the voltage and the angle at bus 2 using Newton-Raphson method, and we will solve it for 2 iterations. So now let me write the power flow equations, and even before that let me write the general form. As we know that the admittance have only susceptance, because we know that y you know that y is equal to g plus minus jb. This is susceptance, this is the conductance. So as the conductance is 0, so we have only susceptance of the transmission line. So now the general form of the power flow equations, we discussed that the power flow equations, depending on whether the admittance is given in rectangular form or in the polar form, the shape or the format or the style of the power flow or the shape of the power flow equation are different. So now let me, as the only substance is given, so let me first write the, so now we will solve the first task, that is A. But even for writing power flow equation, we did those calculations which were important, because in the power flow equation you will see that admittance is important. I mean, admittance appear there, that's why we have to find first the entries of the power of the bus admittance matrix. So let me write the general form, that is equal to so P at any bus k will is equal to sum of all the terms j start from 1 to n, uh, u j u k, and then g k j cos of psi kj minus, oh sorry, plus b k j sine of psi kj. And similarly we have the expression for the reactive power, that is equal to j start from 1 to n, uh, u j, which is the magnitude of the voltage at bus j, the magnitude of the voltage at bus k, the conductance between the two buses k and j, sine of psi kj, which you remember this is the subscript which mean the difference of the angles, psi k minus psi j, we put it as kj. You now this, I mean, from the discussion we have already met. So that is bkj, the negative sign, cos of psi kj. So now as j vary from 1 to n depending obviously on the number of buses in a particular network, as the problem we are solving have only two buses, so it means they will vary from 1 to 2, so it's only two bus system. So now let me write the power flow equation, and it was mentioned here that write the power flow equation for the active and reactive power, that is P2 and Q2, which is the powers on the load bus. So let me now write the expressions. So for k equal to 2, P2 will be equal to they vary from 1 to 2. So now we will have j is 1, so that will be u1, and k is 2, so that will be u2, and this term is 0 because conductance is 0, we have only susceptance, which means that this term will appear. Sorry, I'm talking about the active power, so this term is 0 and only we will have the sine term, and bkj, which is b21. So as I mentioned, we need basically the bus admittance matrix in the beginning, because that value we determine from the bus admittance matrix. So now b21, which is b21, so that will be in this value, which is the first element in the second row. So that will be equal to 3.22, but anyhow we can even write it either b21 or we write directly the value, so that will be equal to 3.22 sine of psi 21 plus because these are the summation of the terms. So now k equal to 2, we have write for j equal to 1, and now j will be equal to 2. So if j is 2, it means k is already 2, so this will become u2 square, because k is 2, j will also be 2, so that will be equal to u2, the square of this term, into as this term is 0, so that will be B22, which is we know that this value is minus 3.22. You see, B22 is minus 3.22, so that will be equal to minus 3.22 sine of psi 2 2. Okay, as k and j both are 2 2. So this is the second term and that is the first term. Similarly, we can write, but even one can either put the value or one can even put, let's say this is B21 and that is basically B22. So whether you put the substance or you put directly the value, that is depending on you. But anyhow, now let me write the expressions for the reactive power. So now Q2 will be equal to, one look here, K equal to 2. It will also have two terms. As this term is 0, so it will have only B term. So that will be equal to again U1, U2, U1, U2 and into this will be again B21, which is 3.22, but we have a negative sign, you see, so that will appear here. So we will have a negative sign in front and then 3.22 and cos of psi 2 1 plus once again as j is 2, so this will be u2 square into B22, it is negative and we have also a negative sign here. Clear? So that will become positive. So then we have B22, so that will become 3.22 and cos of psi 2 2. So now these are the expression for the active and reactive power. These are the expression for the active and reactive power at bus number 2. So we have now solved the first task, and now let's proceed to the second task. And for second task, as it is related to the the voltage calculation, at the bus number 2 using Newton-Raphson method. So we have to follow all the steps which I summarized in the beginning of this lecture. So we will now follow all those steps. So now by doing this exercise, I hope it will make your understanding more clear about or related to this particular method. So now let me proceed to the second task. So the second task is related to the calculation of the voltage. So the second task is to calculate U2 with angle psi 2. Let me make it using Newton-Raphson method. Newton-Raphson power flow method. So we will do two iterations. Clear? So two iterations need to be performed. Two iterations. So two iterations need to be performed, and we have to find the voltage magnitude and the angle at the load bus using this method. So as I mentioned in the beginning that if one look to the steps, we have to make an initial guess and then we have to find the error. So all this algorithm is based on, or all this algorithm is for calculating the error in the first estimate. So we have to find the error. This algorithm is all about finding the error in the first estimate. And as I mentioned that for finding the error, this is the compact form of the Newton-Raphson method. So we have to find the Jacobian matrix involving the derivative of the powers with respect to the voltage and with respect to the angle, and also the power mismatches. And then once we know these two, we will calculate the error. So it means that we have to find the power mismatch, also the Jacobian matrix, and once we know these two, we will find the error in the voltage and in the angle that we make we initially guess these values. So now let me first find the or let me write the compact form of the Jacobian method. So this side, on this side we have the on this side, if you remember, on this side we have the power mismatch. This is the Jacobian matrix and that is the error. So now let me write that we, as this is a two bus system, so the Jacobian matrix or the Newton-Raphson method, we can write it like that: delta P2 and delta or error power mismatch, that will be equal to, as per this discussion which we have made yesterday, this is the power mismatch, this is the Jacobian matrix, and that is the error. So now for two bus system, you know, it will have 2n cross 2n entries. N is 2, 2 cross, that will mean 4 cross 4. So we will also write the Jacobian matrix, and then also I will discuss that how we can reduce the size, or depending on the given parameters, the given values, and knowing the specifications of the different buses, how can we reduce this matrix. So that we will also discuss. But anyhow, let me first write that we have the Jacobian matrix here. So let me write it as Jacobian matrix. So this will be the Jacobian matrix, and then we have the error, that is the error in the angle and the error in the voltage U2, because we are supposed to find the problem is to find the voltage and angle at bus 2. Clear? So that's why I have to find also the error in the power mismatch at bus 2 and also the error in the first estimate. This is the Jacobian matrix. So now let me even write now the Jacobian matrix. As I mentioned that it will have 4 cross 4 entries. N is 2, number of buses are 2, so this will become 4, that will also become 4. So let me write first the Jacobian matrix. So the Jacobian matrix will look like that. The Jacobian matrix, which is this one, that can be written now. The Jacobian matrix will have 16 elements or 16 entries. So first, if you remember here, that is the first entry. The derivative of the active power with respect to the angle, and here we have these entries where we take the derivative of the active power with respect to psi 1, then psi 2, psi 3, psi 4 up to psi n, and similarly the derivative of the same expression with respect to the voltage u1, u2, u up to un, as we have two bus system, so that will be obviously psi 1 and psi 2, u1 and u2, and then we have the derivative of the power at the other bus, which is, let's say this is bus 1, that is bus 2, so that will be derivative of the power, active power at bus 2 with respect to psi 1 and psi 2, and then the same, and then we have also the derivatives of the reactive power with respect to the angle and with respect to the voltage, and similarly for the bus number 2. So as I mentioned, it will have 2n cross 2n elements. We know that the number of buses in this particular network are 2, so it means that the matrix we will have for this particular problem will have 16 elements. So let me now write the first entry will be equal to the derivative of P1 divided by the derivative of P1 with respect to the angle 1, and now the second entry will be the derivative of P1 with respect to psi 2. Similarly, we will take the derivative of the power with respect to U1 magnitude and the derivative of the power P1 with respect to the voltage magnitude at bus number 2. Clear? So now we will also have the other entries. These are the 4 entries. Similarly, now this was P1, so we will have now for k equal to 2 or for the other bus. So let me now write that. So that will be equal to P2 delta psi 1 and then delta P2 delta psi 2 delta P2 U1 and P1 P2 and U2. Similarly, we will have the row for the reactive power, that is Q1 over delta psi 1 Q1 psi 2 and Q1 over U1 magnitude and then Q1 over U2 magnitude, and the last entries will be Q2 over delta psi 1, let me put it like that, then Q2 over delta psi 2 and then Q2 with respect to the voltage magnitude and then same with respect to the voltage magnitude at bus number 2. So now this will be the Jacobian matrix having 2n cross 2n elements, and as n is 2, so it will have 4 cross 4 elements. These are the number of elements in this particular bus. Now as I mentioned that we have to reduce the size depending on the given values, parameters, and also knowing the specifications of the different buses. So as we know that for the slag bus, as we know that for the slag bus, which is bus number 1, as bus number 1 is the slag bus. So if bus number 1 is the slag bus, it means that we don't know the active and reactive power at this particular bus. So if we don't know the values, what we do, because the slag bus is not it is not specified for the active and the reactive power, you know that by the definition, and we discuss it in the class. when we start discussing the power flow equations and the power flow problems. We already discussed the different types of buses. So as the bus number 1 is not specified for the active and the reactive power, it means that we will now remove one row so this row, it means that this row will be removed for P1, and similarly for the Q1 this row will be removed. Clear? As we don't know or it is not specified for the active, because we, as you know, by definition the slack bus is the bus which also account for, or when we calculate the losses, so it is assigned to the slack bus. So anyhow, we discussed those concepts before, but now we are just using those concepts. So once again, also at the slack bus, because we know at the slack bus the angle psi 1 is, that will be 0 degree. We know at the slack bus the angle is 0. Also at the slack bus, in the per unit, we take U1 equal to 1 per unit, that we know by definition. So the magnitude of the voltage will be equal to 1 per unit and the angle will be 0. So now it means that we can also now, as psi 1 is 0, so it means we will also now remove one column for psi 1, and also we know the magnitude at the slack bus, the voltage magnitude, so also this column will be removed. So the remaining entries will be this one, this one, this one, and this one. Clear? So that's what I discussed yesterday, even that depending on the the network, and also depending on the nature or the type of the buses and the given information, we can reduce the size of the Jacobian matrix. So now it will be a 2 cross 2 bus, a 2 cross 2 matrix. So that now the Jacobian matrix will look like that. So we are solving part number 2 or task number 2. So we are solving task number 2. So let me first adjust the page. So yeah, so that we are now solving task B, and now the Jacobian matrix will look like that. The Jacobian matrix will have only 4 entries, with that will be the derivative of the power with respect to psi 2 and the derivative of the power with respect to U2 magnitude, and similarly the other entries will be the derivative of the reactive power with the derivative of the reactive power with respect to the angle, and the derivative of the reactive power with respect to the voltage. So this will be the with having 2 cross 2 elements. So now that is the Jacobian matrix with 4 entries only. So now as I mentioned that we have now determined the Jacobian matrix. Now the next step is to find the power mismatches. And once we know, because we have determined the Jacobian matrix, we will now find the power mismatches. So now let's first find the power mismatches. As the power mismatch, if you remember, we discussed it yesterday, that the power mismatch at a particular bus K is equal to the known value minus the estimated one. Clear? So now let's talk about this one. We will now calculate the power mismatch. So delta P2 will be equal to the noun value at bus number 2 minus the value that we will calculate based on initial guess. So now that will be equal to P2 noun value minus the value that we will calculate based on the guess. And if you remember, we write in the beginning we write the expressions, or we wrote the expressions for the active and the reactive power. So that was basically the expression for the uh, active power, and that is the expression for the reactive power. Let me even mention also here that because at the Slake bus we know that, so at the Slake bus we know that the voltage magnitude is 1, the angle is 0. So it means that this will become 1, and this angle, as the angle is 0 and the sine of the same angle, so it means this term will become 0, as this is psi 2, because psi 2 is psi 2 minus psi 2, and the sine of the angle is 0, so it means this whole term will become 0. And here for the Slake bus, let me first write these expression, that for the Slake bus these expression will reduce to. So for the Slake bus now, for k equal to 0, which is the, sorry, for k equal to 1, which is the Slake bus, that is the Slake bus where the voltage magnitude is equal to 1 and the angle at the Slake bus is equal to 0. So that is, we now by definition. So now for this, if we put these values here now, it means P2 will have only one term, because this term will become 0. It will only be this term. And if you remember, if you look here, U1 is 1, and this will become only 3.22, which is minus 3.22 U2 magnitude and sine of psi 2. Clear? So this term can be written because U1 is 1. Similarly, Q, if one look to the Q2, now Q2 can be, as U1 is 1, so this term can be now delta Q2 can be written as Q2 minus this term where U1 is 1, so that will become minus U2 and into 3.22 cos of as this is psi 2 minus psi 1, which is psi 1 is 0, as psi 1 is 0, so this will become cos of only psi 2. Clear? Minus the other term, which is this is the other term, which is, now this angle will be cos of the this will be cos of 0, because this is the same angle, so that will become minus sorry, that is plus here, that is not minus, that is plus term here, which is U2 square into 3.22. So now we will get it as that will be because Q2 at the load bus is 0, that is given in the problem. Q2 is 0. So we know that in the problem it was mentioned that the Q2 is 0. So it means if we put it 0 and then we also multiply the negative sign, so that will become minus 3.22 u, sorry, this is square, as I mentioned, this is the square term. So now that will become 3 point, as it is negative into negative, 3.22 cos of psi 2 minus 3.22 u2 square. So that is Q2 and that is P2. So now we have to find, because for finding the errors, for finding these errors, we have to find the power mismatches. So now let's now proceed after this step. So we have to find the power mismatches, and for power mismatches, as this is the given value, because P2 has been given as in per unit, that is 1. So it means it becomes 1. And if you remember that as it is the load bus, so we also discussed the sign convention. So on the load bus, this will be, as it is the power consumption, so we will have to put a negative sign. So in whole, this expression will become minus 1 minus 3.22 u2 magnitude and sine of psi 2. So now it will become minus 1 because P2 is consumption, so that will become minus, as we have already discussed the sign convention. So now let me now find the delta P2 and delta Q2, because I remember, I discussed that we have to find the power mismatch. We will also have to find the Jacobian matrix, and then we will, from knowing those two matrices, we will calculate the mismatch in the angle. So let me now find the delta P2 and delta Q2. So the next step is to find, as we have already discussed the power mismatch is equal to the delta P2 is equal to this one and delta Q2 is equal to this expression. So now for calculating the power mismatch, we should know the magnitude and the angle. And here we also need to know the magnitude of the angle, the angle and the magnitude of the voltage. And we know that in the flat start, you remember that in the flat start, for the rho equal to 0, you remember, we have already discussed, all these steps when we were talking about the Gauss-Seidel method. So we will use the same knowledge. So now for rho equal to 0, which is, we need to make an initial guess, and you know that in the flat start we assume psi 2 0 equal to 0, and the magnitude of the voltage at the load bus for the, as a guess, will be equal to 1 per unit. You know that already when we were talking about the Gauss-Seidel method. So now it means that this will become delta P2, but now on the initial guess it will become, so now delta P2 for the guess, that's why we put a 0 here. It is not the power, it is just the value for the initial guess of the power mismatch. So that will become, as this is minus 1 minus 3 point, this will is 1, and the this value now will become, if you look here, the angle is 0, so it means this delta P2 will be only equal to -1. So now as the sine of the angle, which is 0, this will become 0, so delta P2 will become only -1. Okay, that will become -1, and delta P2 will become -1, and delta Q2 for the initial guess will become, knowing that it is equal to this expression. So as the psi2 is 0, we made an initial guess and that is 0. So now this will become, the cause of the 0 is 1, so this will become 3.22, and also U2 magnitude is 1. We have made an assumption. So it means this will be 3.22. This is 1 because the cause of the 0 is 1. So 3.22 minus 3, as this is also 1. So now delta Q2 will become 3.22 minus 3.22. So that will become 0. So now we have determined the power mismatches, and we have determined it for the initial guess. So that's why we put 0, 0 here. Next time, when we will know these values, we will update the power mismatches. That is important, and you know that. So because on the initial guess we have determined the power mismatches, and once we will know the values, because it is, these are the values based on the guess, and when we will follow the first step, we will know the values, the actual values, and then we will next time, in the next iteration, we will update these values depending on the value of the psi2, and that is of U2. So now we have found these values, and now we have to determine the Jacobian matrix. We have already discussed this. This Jacobian matrix have these 4 entries, or these 4 elements. The derivative of the P2 with respect to psi2, the derivative of the, so this is now, it means, let me call it the J11. This is, let's say, is J12. This is, let's say, J21, and that is, let's say, J22. So these are the 4 elements of the Jacobian matrix. J11, the first element, the second element, the third element, and the fourth element. Now I will find, because for calculating the error, we have to know the power mismatch, also the Jacobian matrix. So now I have to find the Jacobian matrix. So let me call the first element as J11, similarly J12, J21, and J21 and J22. So now I have to find the J11, which is the derivative of the P2 with respect to psi2. And we have also wrote in the beginning, it was the task to write the expression for the active and the reactive power. So now as we know that we have discussed now that let me once again write it, let me write it that the expression, once we know the given information, let me write it completely, because this was the in the beginning what we wrote was the expression for the P and the Q power at the load bus, but then also knowing the information, or knowing that one of the bus is the slack bus, we can even reduce this expression. And let me write it now. So for k equal to 1, for k equal to 1, what we now is the slack bus, bus P2 becomes, because we have already discussed that the slack bus U1 magnitude is 1, and this is the U2 magnitude, and we know the susceptance value. Also we know that at the slack bus this is psi2, this is psi2 minus psi1. So as the psi1 is 0, so we will have only psi2. So this expression, and this whole term is 0. So it means that for the knowing for the values of the voltage and the angle on the slack bus, we can rewrite this expression for P2. So it will become, so now this is equal basically k equal to 1, which is the slack bus. So P2 will become equal to it will have only this term. It will have only this term. So it will become equal to 3.22 U2 magnitude and sine of psi 2. Similarly, the expression for the reactive power will reduce to, because we know this is 1, and we also know that this angle will be 0, so the cos of the 0 angle is 1, so it will be 3.22 U2 square, and the other term will be negative, this is 1, so this will be 3.22 U2 cos of psi 2, because cos of the this psi 1 is again 0. So the Q2 will reduce to, uh, 3.22 U2 square minus 3.22 U2 cos of psi 2. So now this is basically these are the same expression we wrote in the beginning, but knowing the information on the slack bus, or knowing the value of the angle and the voltage on the slack bus, these two expressions can be rewrite like that. So now this is the the expression on for the active and reactive power on the load bus. So these are the expression, these two are the expression for the active and reactive power on the load bus, knowing the values on the slack bus. So this is the same, these are the same expressions, but now we have used the given information, or we now knowing the information on the slack bus, so these two expressions have been modified. So now as I mentioned that for calculating the error, we have determined the power mismatch. Now we will find the entries of the Jacobian matrix. So now as we know that the first entry of the Jacobian matrix is equal to the derivative of the active power with respect to psi 2, and we know that the active power is equal to 3.22 U2 psi 2. So if you take the derivative of this term with respect to psi 2, it means that this term will become cos, and U2 will be taken as this will appear as it is. So only this term, this will become cos. Similarly, we can write J12, which is the derivative of the P2 with the derivative of this expression, with respect to U2. So these are quite simple derivatives, but let me even write it. So now we will write basically J11, J12, J21, and J22. So now as I mentioned that we have to find the Jacobian matrix J11. So the first entry of the Jacobian matrix is equal to the derivative of the active power with respect to psi 2. So that will become, and knowing that P2 is equal to, P2 is equal to 3.22 U2 sine of psi 2. So this will become 3.22 U2 again, and cos of psi 2, because the sine term will become cos. Similarly, J12, the second element, or the second element of the first row. So now we have to take the derivative with respect to U2. So now if we take the derivative of this expression with respect to U2, it means it will only become then 3.22 and sine of psi 2, because U2, if you take the derivative with respect to U2, so it means it will become 1. So now that will be equal to the derivative of P2 with respect to U2 magnitude will become equal to 3.22 sine of psi 2. So similarly, the other derivatives can be taken. That is the derivative of the reactive power with respect to psi 2 and the derivative of the reactive power with respect to u2. And we know the expression for the reactive power. So using this expression and taking the derivative of q2 with respect to psi 2 and with respect to u2, you can do it yourself. Let me just write it. So J21, which is the derivative of the q2 with respect to psi 2, so that will become equal to 3.22 as we are taking it with respect to psi 2, so this term will become 0. Only this term will appear, and that will become, and we know the derivative of the cos is minus sign, so that will become positive. So 3.22 u2 and sine of psi 2. Similarly, J22, which is the fourth element of the Jacobian matrix, that will be the derivative of the reactive power with respect to u2. So that will be equal to, now this will be, because it's square, so that will become 2 times into this value. And similarly, this we are taking it with respect to u2, so this term will also, let me take the derivative of this expression with respect to u2, so it can be written as like that, because 3.22 is common as it is appearing in both the terms, so we can take it common. So that will become 3.22 2 u2 as it was the square of the u2 minus cos of psi 2. So now we have determined all the 4 entries. As I mentioned, we have to for calculating the error in the first guess, we have to now the power mismatch, which we determined, and afterwards we determined the Jacobian matrix. We reduced it. After reduction, we know that it has 4 cross 4 elements. These were the elements of the Jacobian matrix. After reducing it, knowing the angles and the voltages, the angle and the voltage on the slack bus, so, and also knowing that the active and reactive power is not specified on the slack bus, so the size of the Jacobian matrix was reduced to 2 cross 2 elements, and then we determine we took the derivative of these powers with respect to the angle and with respect to the voltage, and we have now determined the 4 entries which are equal to this one. Now once again now, knowing that for the flat start, once again, as we determine the power mismatch, for the flat start. So we put it a 0 here. So we determine that the power mismatch for the active power is -1 and for the reactive power is 0. Now we will exactly use the same information for the flat start, and now we will determine the Jacobian, but now let me for the flat start, and you know what flat start means. So now J110, meaning to say that we are calculating now the entries of the Jacobian, or the elements of the Jacobian matrix for the initial guess, as we have made a guess that psi 2 in the flat start is 0 and u2 is 1. So this term will become this term will become J110 will become 3.22, and J120, which is this term, will become 0, because if we put psi 2 equal to 0, as we know that in the flat start we assume the angle as 0, the voltage magnitude as 1. So as I mentioned here, that in the flat start the angle is 0, the voltage magnitude is 1 per unit. We are making all the calculation per unit, so this will become sine. When you put sine of 0, this will become 0. Similarly, the J21 with the, this is means that for the initial guess of the values, this is not the power. Once again, you know that. So this will become once again 3.22 as this will, sorry, this will become once again 0, and this term, the last term, it will become, because we know that this will be, this is the psi 2 which is 0, so this will become 1, and that is also 1 because the magnitude is 1, so it is 2 minus 1, so which is 1, so it means 2 minus 1 is 1 and 3.22, so the J22 will become 3.22. So now we have even determined the 4 entries of the Jacobian matrix. We have also determined the power mismatches. So now, knowing the power mismatch, knowing the Jacobian, the entries or the elements of the Jacobian matrix, we can now calculate. We can now calculate. Oh yeah, we can now calculate the, knowing the Jacobian matrix, knowing the power mismatch, we can now determine the error in the first estimate of the angle and that of the voltage, because we know the values of the entries of these two matrices. So the next step was to take the inverse of this, because to know these values we have to take the inverse of the Jacobian matrix and multiply it with the power mismatches. So now what we will get, we have to take the inverse of the Jacobian matrix. We have to take the inverse of the Jacobian matrix and multiply it with the so now delta of the error in the angle and the error in the voltage magnitude will become equal to Jacobian 0. Why I put 0? Because we have determined these values for the initial guess, so that's why I put 0 here. Once we will update these values, as I mentioned even in the power mismatches, once we will update these values based on the values of the angle and the voltage, then we will put 1 here, because we have determined now these values for the flat start. That's why I put here 0. You know all this information from the previous discussion. So now J0, which means that this is the Jacobian matrix for the initial guess of the voltage and angle. So now we have to multiply it with the power mismatch, so which is equal to delta P to 0 and delta Q to 0. So we have to take now the inverse of the Jacobian matrix. So we know the entries, which is 3.22, 0, and 3.22. So let me now write basically the, let me take the inverse of the Jacobian matrix. So we know the Jacobian matrix, knowing, let me first write the Jacobian matrix for this one, and then I will take the Jacobian inverse. So the Jacobian matrix will have the following 4 elements that we have determined before. 3.22. These are the entries. 3.22, 0, 0, and 3.22. So now this is the Jacobian matrix, and now we can find the inverse, so that it will be multiplied with the power mismatches to get the error in the angle as well as in the voltage. So you know that the inverse of a matrix is equal to the 1 over the inverse of a matrix is equal to, so the Jacobian inverse, so the inverse of the Jacobian matrix will be equal to 1 over determinant of the J0 into the adjacent, sorry, I need to put adjacent here, adjacent of the Jacobian matrix. So we know that the determinant is equal to the product of the these two terms. You know that from mathematics quite in detail. So that will be equal to, so the determinant, this term, the determinant will be equal to J11 into J22 minus J12 into, so that will be equal to J11 into J22 minus J12 into J21. So that will be equal to the determinant, and then the adjacent of this matrix will be equal to the adjacent, which is this term, that will be equal to the adjacent will be equal to the adjacent will be equal to so the adjacent will be equal to the adjacent will be equal to we know that from the previous discussion. So we need to change the position of these two terms and the sign of these two terms. So I mean these two are equal, so even changing the sign will not change anything here. So I don't think so I need to write it. So that would be, I mean, let me still even write it, but anyhow that will be the same matrix. So that will be 0 and 3.22. So because these two terms are equal and these two are 0, so nothing will change even after taking the adjacent. So now let me actually this term will be equal to, if we multiply these two terms, this is 0, so this term will be equal to 10.3684. so this will be the determinant and the adjacent. So now the Jacobian, the inverse of the Jacobian matrix, let me write it directly rather than going through the calculations, because you know this quite well. So that will be then equal to let me write just the final matrix. So that will be equal to 0.310500 and 0.3105, as these two entries were equal. So dividing now each of these entries with this term or this factor or this value, we get the inverse of the Jacobian matrix. For 2 cross 2 it is quite simple. I believe it will take more time when the order of the matrix gets larger. So now, as you remember that we discussed that we need to know the Jacobian inverse, and we have already calculated the power mismatches. So now just putting the values, taking the product, we will know the we will know the error in the angle as well as in the voltage. So now this will be the, so now taking the, I mean writing it in this form. This is the Jacobian inverse, which is this matrix, and the power mismatches we have calculated before. That was equal to 1 was the power mismatch of the, I mean for the active power it was -1, and for the reactive power it was 0. So now we know the inverse of the Jacobian matrix. So I will directly write it like the error in the angle and the error in the voltage magnitude will be equal to the Jacobian inverse, which is the same as this matrix 0.3105 0 0 0.3105. So now taking the product with the power mismatch, which is equal to -1 and 0, so we will get the value. I will just write you now how to get a multiplication of the result of the multiplication of the matrices. So I will not go through each and every step, but rather I will write it directly. 0.3105 and the other value is 0. So now we have found the error both in the angle as well as in the voltage. And if you remember, we discussed that for taking the next step, what we need to do is that we have to add the error in the first estimate to get the next estimate. Similarly, the case of the voltage, and this is the case of the angle. So we now know the error both in the angle as well as in the voltage. We have made the initial estimate. We will add those values to get the next estimate. So now I will follow this step. We have already discussed all these 6 steps, and now this is the 7th step. So now the next estimate will be that psi 2 1. If you remember, in the first estimate, in the flare start, we assigned a value. If you remember, we assigned a value of 0. That was for the flare start. We put psi 2 equal to 0 and u2 1 per unit. Now I will add to the initial guess the errors. So it will now become 1, and that will be psi 2 the initial guess plus the error in the guess. So delta psi 2 0. So that will be now equal to, this was 0 and that is minus 0.3105. So this will become, if we add even to this one 0, nothing will change. So that will be minus 0.3105. This is in the radian. This is the radian, and if we want to convert it into the angle, so that will be equal to, or maybe one can convert it, but anyhow I think one can get it also in the degrees. Similarly, u21 will be equal to u20 plus the error in the magnitude that we have calculated, and this is equal to 0. So even adding, so this will remain also 1 per unit because this value is still 0. So this is now 1 per unit. Now we have completed one iteration. And now for the second iteration we will use the updated values. As in the first iteration we used voltage of, means in the first guess that was 1 per unit and the angle was 0. Now for the second iteration we will now use the updated values, although the voltage remain the same because we found that the error was 0, but the angle is no more 0. The angle have a certain value now. So now we will use these values for calculation, for further calculations, or for the second iteration. So now let me proceed with the second iteration. And as you remember, the steps are that first we have to calculate the error, because for calculating the errors we should know the Jacobian matrix. We should know the Jacobian matrix as well as the power mismatch. So I will first calculate the power mismatch based now on these values, because initially we calculated the power mismatch. If you remember, we calculated the power mismatch. Let me find that page. So the power mismatch was equal to the which was equal to the difference of the given value minus the difference of the given value minus the calculated results. So let me find that value. Where is that? information, yeah, here. So now we have already I mean this was the expression for the delta p 2 and delta q2, and once we took, if you remember, when I mentioned the flat start, so we calculated that delta p2 was -1 and delta q2 was 0. Now if I put here because when we put psi 2 in the flat start, that was 0, this term was 0, that's why, and this was given, and according to sign convention it was -1. So because this term was 0, so it remained only -1. Similarly delta q2, because this was 1 and this is also the magnitude of the voltage was also 1, so the result for delta q2 0 was 0 because the two terms were equal, and in between we have a negative sign, so that's why the result was 0. Now if we put in this expression psi 2, which is equal to, now it is no more 0 but rather we have the value that is equal to -0.3105 radian. So now I will put this value here to get the power mismatch, and now I will not call it delta p2 0 but rather it will be delta p2 1, because now I am using the updated values of the angle, and similarly I will call it delta q2 1. So now, and similarly now you see this will be no more 0 because now psi 2 is not 0, although u2 is 1 but psi 2 is no more 0. So let me now first find the power mismatches, then I will find the Jacobian matrix, and we have already we know that the Jacobian matrix entries are these ones. So I will just now, you see, I mean now the further calculation will be simple because I will now use the updated values of the angle and that of the voltage which I know. So just putting those values I will get the Jacobian matrices, and also putting, I mean, the updated values of the power of the angle and the voltage magnitude, I will also get the power mismatches. So let me first calculate the power mismatch and then the Jacobian matrix for the next iteration. So now let me proceed with that. So now I will once again, you knowing that this is equal to minus 0.322 u2 and psi 2. So now let me write the expression first, but now knowing that psi 2 1 and u2 1 is having these values, so now I will put now delta p2 1, which is equal to -1 minus 3.22 u2 magnitude and sine of psi 2. So now taking u2 equal to 1 per unit and psi 2 1 as 0.3105 radian, so I will get it to be equal to minus 0.01617. Now if we compare, in the beginning the power mismatch was quite high. You see the power mismatch was 1 per unit based on these values, but now using the updated values, when u2 is 1 per unit and psi 2 have a value of minus 0.3105 radian, putting these two values, now the power mismatch has drastically decreased from -1 to minus 0.01617. So you see, and now similarly I will determine the delta q2 1, which was equal to, if you remember, that was equal to 3.22 cos of psi 2 minus 3.22 u2. Now this is 1 but this is no more 0. So now putting the updated value of the angle and that of the voltage, I will get, as it was equal to 3.22 cos of psi 2 minus 3.22 u2 magnitude square. So now putting this one as, I mean, the angle which we have determined, that should be now 1, that should be now 1, that should also be 1, and that should also be 1. It should no more be 0. The updated values must be used. So now this will become equal to, this will be equal to, after putting all the values, it will be equal to minus 0.1539. And now if we compare to the previous case, you see the mismatch of the active power was minus 1, the mismatch of the reactive power was 0. Now the mismatch of the active power has drastically decreased from minus 1 to this value, and the mismatch of the reactive power is no more 0, it is minus 0.1539. So now we have determined the power mismatch. The next step is to find the Jacobian matrix, but we know the Jacobian, I mean the entries of this matrix are equal to these ones. So I will just use now exactly, I mean it will be no more the estimated values, but it will be now the updated values of the angle and that of the voltage. So now putting the updated values, we will get the entries. And if you see here, the J1 was equal to 3.22, J12 was 0, J21 was 0, and J22 was also 3.22. Now after using the updated value, let me now find again. I will rather directly write it, because you can do it yourself, as this is equal to 3.22 U2 cos of psi 2. The previous case this was 1. In the flat start, the angle was, we assume it to be 0, so that was 1, and we assume the voltage to be 1. But now psi 2 is no more 0, it has a value of minus 0.3105 radian, and the voltage is still 1. So now putting the angle and take it still 1, we will not get any more 3.22. Similar is the case for all these entries, for all the Jacobian, for the the elements of the Jacobian matrix. So putting now the updated values, that of the angle and that of the voltage, we will get the new elements or the new entries. So now based on the updated values, I will get the Jacobian matrix. And if you remember, initially I put 0 here, that was the Jacobian matrix for the initial guess. I will no more put 0 here, rather I will put 1 here. So you see, initially I put a value of, if you see here, I put a value of 0 here, and then I took the inverse of that matrix. Now I will put here now 1, because I will use the updated values of the voltage and that of the angle. So it will be equal to, I will rather directly write those entries, so that will be J111, J121, J211, and J221. So that will be equal to, you can do the calculation yourself. So J11 is, this matrix will now be equal to, so this matrix will be equal to, this matrix will be equal to, this matrix will have entries that is equal to 3.066 and minus 0.9838. This is the same value, minus 0.9838, and this value is equal to 3.3739. So now this is the updated values of the Jacobian matrix. If we compare it to the previous case, the entries were 3.2200 and 3.22. Here we have different values, because now we are using the updated values of the angle as well as that of the voltage. So now the Jacobian matrix, the new entries we will take now, because we have determined the power mismatch. The other important step is to determine the inverse, or take the inverse of the Jacobian matrix. So I will not go once again through those steps, but you know how to take the inverse of a matrix. So I will directly write the inverse of this matrix. So the Jacobian one inverse will be equal to, it is one will determine into the adjacent of the matrix, where we change the position of these two and then change the sign of these two. So it will become positive positive and will move here, this value will move here. But anyhow, you can do that yourself, and I will directly write the inverse of the Jacobian matrix. So this will be equal to 0.3598 and 0.1049 and 0.3269. So now this is the new matrix. If you remember, the previous one was equal to you see, the previous one was having two entries 0, and these were the inverse of the Jacobian matrix based on the initial guess. But now, based on the updated values of the voltage and the angle, there are no more 0 elements, and all the values are different compared to the previous case. So now this is the new Jacobian, the inverse of the Jacobian matrix, and now I will take a product of this matrix and the power mismatch, because for calculating the error in the angle as well as in the voltage, we need to take the product of the Jacobian, the inverse of the Jacobian matrix into the power mismatches. So now I will use the updated values and I will get the power mismatches. So now the power mismatch will be equal to, let me write it, the power mismatch delta psi 2. Now I will put 1 here, delta u2 1. This will be equal to now the Jacobian inverse into the power mismatches, delta p21 and delta q21. We are following exactly the same steps, but now the values are updated. So in the previous case, we found the psi 21 and we calculated the error, but those iterations were 0 0. Now it will be, we have determined now, and if you see here, we put the delta p0 and delta q, we put here delta p0 and delta q0. This was also with the 0. Now it is 1 1 1, and similarly this was the 0, the error in the first iteration, so that was 0 0. Now it will be 1 1. So now let me directly write it. So the error will now, after taking the product, we have determined all the values I have wrote. This is the Jacobian, this is the inverse of the Jacobian matrix, these are the power mismatches. So now taking the product of this matrix and this one, this is the matrix, we know these power mismatches. So now taking the product of this matrix with these values, we get the that is equal to, so delta psi 21 and delta u21 will be equal to, taking the product, so the final result will be equal to minus 0.02196. You can do the calculation yourself. You can take the product of those two matrices. I will directly write the values, 0.0526. Now if we compare it to the previous case, that was you see here we have, in the previous case there was the error in the angle was this value, and there and the voltage was 0. Now based on the updated values, the error is for the angle is this value, which have changed from minus 0.3105 to minus minus 0.02196. So from 0.3 it has changed to 0.02, and similarly the difference has changed from 0 to minus 0.0526. So now I can, exactly following the same steps, now I will determine psi 2 2 and u 2 2. So now psi 2 2 will be equal to psi 2 1 plus error in this value, which is delta psi 2 1, and now adding, because psi 2 1 was equal to, if you remember, psi 2 1 was equal to this value, and now the psi 2 the error is this value. So adding now this value with this value, we will get the final value, that is equal to, so it will be equal to now minus 0.3105 minus 0.02196. So this was the psi 2 1, and this is the error. So adding the two, now we will get the next estimate. So that will be equal to minus 0.3324, which is equal to minus 19.04 degrees. Similarly, we will get the u2 for the second iteration, that will be equal to u2 1 magnitude plus delta u2 1 magnitude. So I will just write the values. Now it was equal to 1, and adding it to this value, so 1 minus this value will be equal to 0.9474 per unit. You see, this one was equal to 1. If you remember, u21 was equal to 1 per unit. Now adding it to this value, having a negative sign, so adding 1 to this value will become 0.9474 per unit. So if you remember, the question was, we have completed now the two tasks. The question was to write power flow equation for this particular network, or for this particular case. Write the power flow equation for active and reactive power, and then calculate the voltage magnitude and the angle using two iterations of Newton-Raphson power flow method. And we did all the calculation in the per unit. So now we have determined the voltage magnitude as well as the angle for two iterations using Newton-Raphson method. So these are now the final values. So as you let me even now once again go through the steps. I mean, in the beginning, what we did, we made an initial guess. Then afterwards, we use these values and we determine the power flow equations. What we wrote in the beginning. Then we use the estimated values to find the power flow equations. And knowing the values of the active and the reactive power on the load bus, we took the difference. This was the given value. This was the calculated based on the initial guess of the values, that of the angle and that of the voltage. We determined the error. We took the then we calculated the power mismatch, and afterward we differentiate the power flow equations. I mean, all this discussion we have carried. So we then took the derivative of the equations with respect to the angle and with respect to the voltage, and we determine the entries of the Jacobian matrix. And so we calculate the Jacobian matrix, and then using the estimated values, we even found the values of the Jacobian matrix, or the values of the entries of the Jacobian matrix. And you know that in the initial guess, these values were like that, and then once we found the updated values of the angle and that of the voltage, these values changed. So then we invert the Jacobian matrix, because for determining the error in the angle as well as in the voltage, we need to know the power mismatch and we need to know the inverse of the Jacobian matrix. So as I mentioned, we first determine the Jacobian matrix, we took the invert, and then we took the product of the two to get the error. And once we determine the error, we added that error to the guess to get the value for the next step. So, and then we use these values for the next step, and we did all the calculations. So now I have completed those two tasks, or we have now solved this particular task for two iterations of the Newton-Raphson method, and the final results were determined to be equal to, you see. So these are basically this is the voltage now, the voltage magnitude, and this is the angle. And if one want to carry the third step, I mean all those steps will be exactly the same. One has to first find delta P2, but this will be 2 now, because now one will use the updated value of the angle as well as that of the voltage. And similarly will be the case of the Jacobian matrix. Now it will be 2. And once these two are determined, it will be also 2 and 2. So with the 2, we will add the error to get the psi 2 3 and u2 3. I mean, if one is interested in the third step, he or she can carry even the third step. So now, as I mentioned in the beginning of this particular problem, that I even tasked you, or I even gave you this problem in the midterm exam, and at that time I asked you to solve this problem using Gauss-Seidel method, and I will just show you the results. I will not basically solve it using the Gauss-Seidel algorithm, but I hope maybe it is clear to you. This is the general form of the Gauss-Seidel algorithm. You know that quite well, and then you know how to basically use this algorithm based on the given values. So you have already carried these steps in your mid exam. But the final results, now once again, you were also supposed to solve this problem even in the mid for 2 iterations. So if I now show you just the final values, if one look here, the U2 magnitude is equal to 0.95, and the angle is minus 17.21. So you see, I mean, just on a one page, or with a little calculations, one can carry basically, one can find the voltage magnitude and the angle when one is using the Gauss-Seidel method. But for finding these values using Newton-Raphson method, the length of each step is quite long. The length is quite long, but the important thing, what I mentioned even when I was discussing the Newton-Raphson method, that it converges faster compared to the Gauss-Seidel method, and one can further probably carry some more steps, because when it is the case of the Gauss-Seidel method, the changes are obvious in each step. But if let's say one take another step after the second iteration, so one will see that the changes might be quite small, meaning to say that the solution has already converged. And if one, let's say, compare the results, so in the case of the Gauss-Seidel method, the angle after the second iteration was minus 17.21, and here we have found it to be minus 19.04, with a difference of more or less 2 degrees, and the magnitude of the voltage was 0.95 in the case of the Gauss-Seidel method, and here it is 0.9474. If let's say one use just 2 digits, so this will become, as you know, the this rule that as it is 7, so it will also become 0.95. So more or less the same value as this one. But I mean the time or the calculations in case of the Gauss-Seidel method are simple, but it takes more steps to converge to a solution. But in the case of the Newton-Raphson method, although the length of each step is quite long, but the number of the steps for converging to a solution are fewer. So I hope with this problem now you have understood the Newton-Raphson method. We discussed in the in the previous lecture the general form of this method. We talked about the Newton-Raphson method, and then in the previous lecture I talked about the Newton-Raphson method, and in this lecture I solved one problem using this particular method. So I hope now all these steps will be clear to you. So I have even revised it quite many times during this recorded lecture. So I hope now it will be clear to you how to solve even a given problem, let's say using Newton-Raphson method. But anyhow, for getting even better understanding, you need to solve some more problems, maybe a 3-bus system, as this was just a 2-bus system. So with that, I hope now this particular power flow method will be clear to you. And even if you have queries, kindly note it down while you will watch the recorded lectures, and we will discuss it in detail in the interactive session. So I hope now it will be clear to you. Thank you very much for your attention. Assalamu alaikum wa rahmatullahi wa barakatuhu.